usage of the signal processing, especially to hearing aid. Okay, so I wish you can take a look by yourself at those two circumstances and give you some ideas about how to implement the signal process to hearing aid. And the ideas actually are very similar to all the other stuff, okay? About say speech process or audio process as well. Okay. So any question up to this moment? Any question? Okay. So this system, this course is talking about the system and the signals. For the signals, it can be divided into two classes. Okay, let's continue. The second one is discrete. Classified into two. Since we are going to use finite computers, so signal. And another one. Now for this course, if we are talking about discrete signal, that means we consider the signal with infinite word length. We don't consider the sampling effect. Okay, we don't consider the sampling effect. Okay? For continuous signal, that's the one you are familiar with, like saying, for example, like velocity, pressure, current, voltage, and so on and so on. Okay? So it creates T to stand for the function of time. Discrete system. For discrete system, we use the notation, say f of n, t, or nts. Okay? Where n can be negative, can be negative. And ts, that's the sampling time. Okay, we will see this in detail later on. So this is the signals we are going to consider. And basically all the systems in nature can be classified into the two categories, continuous or discrete. Okay? For discrete signal, it can also be divided into two different types. One is with finite word length. This is due to the digitization, okay? Because of the computer. Okay, because of computer. Okay. Now, because it is much more complicated if we want to analyze this finite word length discrete signal, it's much more complicated. So that's why we only consider the second one. Okay? We ignore the finite word length effect. Now for a signal, usually we can analyze it either in time domain directly or in the frequency domain. Again, we will see that later in the class. And then, as I mentioned in the course syllabus, we will consider filtering and how to design a filter. Okay? And also how to consider the effect of sampling. This is extremely important when we are considering digitization or when we are considering analyzing the digital signal. Okay? We will see them again and again in the class in details. Okay, any questions before we move on to the next part? Gentlemen, would you mind go to the stationery, purchase a notebook, and then come back ASAP? Now, buy a notebook and then come back ASAP. Okay? Do it now, please. Yes. I need you to take note. Okay? Yeah, please purchase a notebook and come back ASAP. Okay, let's move on to the lecture. In the beginning means we start from the year 1948. That's the first year of digital technology. The first transistor, okay, invented by someone in the Bell Lab. This is the replica, the duplicate of the first transistor that was ever invented. The first transistor. Okay? And then, after that, lots of new technologies were invented. And there's a famous law, it's called Moore's law. What is that? It says that the number of transistors in the chip would double every 2 years. I think everyone knows this, right? Okay? So the number of transistors is going to double every 2 years. And actually, it seems that the speed is faster than this. Okay, for the digital signal process, we need digital signal processor, DSP, and also the FPG. Now, a DSP actually is a mini size. This is the DSP, the structure of the DSP. If you look at the structure of this DSP, you can see that inside the microprocessor or DSP, you can see a CPU, okay? You can see program memory, you can see AD converter, or even a clock oscillator, okay, and I/O port. So a DSP actually is a mini-sized computer. Unfortunately, in this course, we are not going to tell you how to write a code on a DSP chip. Okay, it's not our main focus. We only consider algorithm. Now, if you want to understand a little bit more about the DSP and the FPGA. This is a good website. Okay, in this website you can find the explanation about the digital signal process as well. I think it's written quite well. And lots of insight of the DSP, and also the FPGA. FPGA is kind of a mini-sized board, okay? Kind of mini-sized electrical board. So you can find the explanation again in this website. Even though it's written in Chinese, you can translate it into English very easily. Okay? So Please look at this by yourself at home. All right, now let's go through some simple applications. I think most of them you have already experienced. For example, the first one, CD player. Okay, in the CD player, you can find the digital signal processor. There's a DAC. DAC means what? Digital to analog converter, okay, DAC. Okay, and this is the detailed structure of the CD player. You can find the figure from the World Wide Web very easily. Okay. Also, this one, the software radio. In the software radio, you can find there's a very important subsystem called modulation. Modulator, the modulator means you embed the system. Embed the signal into a carrier wave. Okay, how do you show the signal or show the message? This represents a certain message. For example, this is amplitude 0, 1, 1, 0, 1. Suppose this is kind of a message you want to transmit. And you embed this into the carrier wave. You can either amplitude modulation or frequency modulation to represent the 0 or 1. Okay, so you can see that over here, the first time interval is 0. Okay, so this is the amplitude to represent the 0. And in the second interval, this is the amplitude to represent the 1. And for the frequency, similarly, this is the frequency. Okay, this is the signal to represent the message 0. And this is the signal to represent the signal, message 1. Using frequency or using amplitude, we also are able to convey or transmit the message. Okay? And for aerospace engineering, the most important thing we can see in the air, especially in flight, or even in commercial aircraft, you can see the flight control system. Okay, this is the typical structure, but it's too involved. So let me jump to the closed loop system. That can represent a general system. Okay, for a general closed loop system, this closed loop figure is very important. You can see that it consists of the plant. So this is the one you are going to control. If it is an aircraft, this plant is an aircraft. If this is a CD player, this is the CD player. Okay? And also you have a controller to control the system, to control the plant. In order to take care of the signals, we need sensor to sense, to measure the output from the plant. For an aircraft, this output can be velocity, okay, of aircraft, can be the pressure inside the cabin, can be the temperature inside the jet engine, and so and so. And then in order to be able to process by the digital controller, we need to have a converter, AD converter, to convert continuous time signal, okay, this is continuous time signal, to discrete signal. So this is a continuous time signal, while T, for example. And then after the sampling, we convert continuous signal to a discrete signal. All So we need an AD converter first. And then this AD converter convert the analog signal to discrete signal. We will compare it with our command. Okay, after the comparison, it will be sent to the digital computer or digital controller. Okay, and again, these are discrete systems, cannot be sent to the plant directly. So we have to use a DA converter first to convert the discrete system to continuous time system again. Okay, so this is a typical closed-loop system structure. And this figure is also very important for everyone sitting in this room now. Otherwise, you will be missing, okay? You will miss yourself in this class. What I'm doing here, why we need a discrete system, why we need a continuous time system, and so on and so on. Why we need stuff. Okay? So I highly recommend you to write down this in your note, okay? Usually we also need a clock to synchronize the input with the output. All right? Any questions before we proceed? Again, this is a curve, right? A solid curve. Represent the signal is continuous. Continuous signal. And the dots, they are the discrete signals. Okay, discrete signals. So in general, for a computer control system, you are going to deal with both continuous signal and discrete signal. Okay? So you have to know how to model a clock in continuous time. Also in discrete time, in order to design a discrete controller. Okay? So this is very important. This is a very, very important figure to everyone. So you need to write down this, copy this into your note, so that later on you know what we are doing. Again, I will remind you again and again in the class. Okay? This clock means we need to synchronize those signals. Okay? Everything inside this box. All right, any question before we proceed? Any question? Okay, yeah.
What does the PK stand for?
Sorry.
For discrete signals function.
PK means it is standard at discrete time. Okay, well, okay. This DK, okay, let me give you a simple explanation here very quick. We will see that again, okay, don't worry. Here, let me give you a quick explanation. Suppose I have a signal. Let me call U of t. Okay, it's an arbitrary signal, for example. Now, if I have a sample, that means I take the sample, I take the signal, I measure the signal at every t seconds. Okay, so this is 1t, 2t, 3t, 4t, 6t, and so on and so on. 5t, and then 6t. Okay, so t is the sampling time. That means I measure the signal at every t seconds. For example, t, okay, let me use ts, so in order to be consistent with ts. So that means I measure the signal. Okay, this is the location for the sample. So every t seconds, this okay, in the beginning, the is open. This is open, right? Okay, and every t seconds it is closed. Becomes closed. So whenever this is closed, this circuit is closed, we can measure the signal. We can measure the signal. So we start from t equals 0 seconds, for example. And then let's assume ts is 1 second, for example. Then at t equals 5 seconds, when t is 0, it is closed. After that, this circuit is open. Okay? Nothing in between. And then when t is 1 second again, this circuit closed. So I have another negative. Okay? And repeat the process. So the notation is U of 0, U of 1 ts, U of 2 times ts, U of 3 times ts, and U of 4 times ts. Okay, so this is the notation, right? The U at 1 times ts, U at 2 times ts. But this is a little bit complicated. So we can replace it by U of T1. This is U of, can I use this? So let me use the notation, U of T1 to represent U of 1 ts, and U of T2 to represent U of 2 times ts. Okay, and the U of T3, U of T4, remaining signals. So it is purely a notation for discrete system, for discrete signals, discrete signals. Okay, we will see that again later on. Good. So any other question? Yeah. Any other question? Okay. And so you have asked the question that I'm going to tell you in this slide. Let's take a look here. Okay, now suppose I have a continuous time signal, x of t. Now this x of t can be any signal. It can be the velocity of a particle or the velocity of an aircraft. It can be the pressure of this room. It can be the pressure inside the cabin of an aircraft. Okay? Also can be a current of a circuit. It can be a voltage of a circuit, and so and so. And those are continuous signals. And for the discrete signal, or discrete time signal, okay, one of the examples given in the textbook is the stock market. The price of stock market index, for example, Dow Jones, okay? Or the population a year, okay? The population of this earth, the population of Taiwan, the population of the other country, whatever. They are discrete by year, right? The number of persons also is a finite number, it's an integer. It's an integer. Okay? So it's a finite number. Now if we take the sample, okay, one more time. So now we have sample. And let me zoom in that a little bit. Okay, so suppose this is okay, so that's a sinusoidal wave, actually. So this is the x of t. It's a continuous signal. Continuous signal, right? But then we take the sample at every t seconds. So assume we have a sample, okay, and then I measure the signal at every t seconds. So every time when I take the sample, I have a measurement. So this circle is a measurement. Okay, do you see that? So that's t equals 0. And this is t equals 1 ts. At t equals 1 ts, one sampling time, I have another measurement. When t is equal to 2 ts, I have another measurement. So I can repeat this process at every t seconds. Then I have lots of discrete signals. Okay? So this is the x of, let me tell you. And this is x of 1 ts again, okay? And this is x of 2 ts. And this is x of 3 ts. And this time, then we call this nts. So this nts. Now this is too cumbersome to write down everything here. So suppose we know ts beforehand. So I can use a shorthand notation. So this becomes x0 as well. and I can replace this by and x2, and then x3, x4, x5. Now it's replaced by xn. So we start from x of t, and then we take the sample. Okay, this is the sample. At every t seconds. So after taking the sample, I have x of n ts. Okay? So these circles are the discrete signal n ts. And for simplicity, we replace it by the notation x of n. This is purely for notational convenience. Okay? But one condition, under one condition, we assume you and the me knows what the sampling time ts is. Okay? So you have to know, well, what is the sampling time? Is that 1 second or 0.1 second? Or 0.001 second is always. Okay? All right, let's take a break and then come back after break. 10 minutes break, okay?